Well, hello and welcome to Silicon Photonics Explained, where we'll today be talking about mid-IR silicon photonics and space applications. Without further ado, allow me to introduce you to our fantastic guests today for today's talks, Professor Goran Mashanovich and Dr. Milos Nedjelkovic.
So welcome everyone. As Ramsey said, Milos and I will cover mid-infrared silicon photonics and also silicon photonics for space applications. So I will start and talk for the first 30 minutes and give you a really brief overview of mid-infrared silicon photonics. So of course, within 30 minutes, you can't cover everything. So just give you a flavor of what this field is about. And also I will focus more on the Cornerstone offering, what we can offer to industry academia in terms of mid-infrared platforms. And I also say a bit about results in various waveguide platforms and also in sensing. So this is the outline of my talk. I'll start with a brief introduction. I'll also introduce Cornerstone material platforms. There are 3 of them in the mid-infrared. I'll cover some basic building blocks, waveguides and splitters and spectrometers and so on. And I'll also mention some applications. And I'll finish with some challenges, something that awaits for us in this field in the future work. And at the end, I'll give a summary. So let's start. You will probably find out different definitions of what mid-infrared wavelength range is. And in different communities, it varies, in some cases, quite a lot. So what we in silicon photonics consider as a mid-infrared is a wavelength range from 2, maybe 3 microns up to 20 microns. And why this wavelength range is important? Because as you can see from the image here, it contains a lot of absorption peaks of many molecules, many substances. Here you can see some gases and also some explosives and aromatics and so on. So many molecules, many substances have distinct absorption fingerprints in this wavelength range. And of course, the first thing we can expect is that we use this wavelength range for sensing. But you will see that we can use that also for other applications. So what I mean by unique fingerprint absorption is shown on this slide. You can see 3 gases, which we're talking a lot about recent times because of climate changes and so on. So we have carbon dioxide, methane, and nitrous oxide. And we are showing here transmittance as a function of wavelength. And you can see that all of them have very different absorption peaks. So we can uniquely determine which gas is present in an environment. How we can sense these gases? We can use 3 paths between source and detector. In some cases could be meters or tens of meters if we want to detect small concentration of these gases. Or what we're really interested in is using integrated silicon photonic chips that may have source and detectors and electronics all integrated in the same chip. And then we have waveguides, and through evanescent field of an optical mode that goes through that waveguide, we can detect presence of these gases. I've just told you that it's not just sensing, but let's start with some of the main sensing areas. So probably the most important one is healthcare, where we can analyze blood or breath, get some indication of certain diseases or of certain conditions before going to some thorough investigations. We can also use potentially silicon photonic sensors for monitoring air quality in hospitals or for imaging of tissues. One image is, for example, shown here. As I already mentioned, we can monitor greenhouse gases, air quality in cars or in rooms, or water quality, which is becoming an extremely important field. We can also detect presence of some dangerous materials. We can also use sensors, mid-infrared sensors in process control in industry, and also in transport to monitor, fuel consumption or emission of certain gases and so on. But there are some other also very important fields. I'll mention three of them. First, agriculture. We can detect presence of some toxins in food, so that's very important. It could be kind of screening, where we screen nuts or grain in some big storages to get an indication if there is a presence of toxins, and then use some more accurate methods to actually determine what's the concentration or what toxins are actually present there. We can also use mid-infrared photonics in communications, because mid-infrared has two windows, transmission windows, from 3 to 5 microns and from 8 to 12 microns. So we can use that for communications channels. And also astronomers are interested, especially around 10 microns, to image some planets. So there is a lot of scope for the mid-infrared photonics. When we come to the materials that we can use, this nice image from MIT shows different groups of materials, and obviously we're interested in group 4. So we have silicon, which is transparent up to roughly 8 microns, germanium from 2 to 14, 15 microns. Diamond is also group 4. It's very good material because it's chemically resistive, so it can be used for sensing of various analytes. We can also use nitrides. We're especially interested in silicon nitride, which actually we consider as a group 4 material. 3,5s also have large transparency ranges, gallium arsenide or indium antimonide. Chalcogenides, I'll mention a couple of them: zinc selenide, cadmium telluride that we use here at Southampton, or halides like calcium fluoride, which we use as windows in the mid-infrared. The main advantage, obviously, of group 4 materials, and I'll cover mostly silicon and germanium today, is low cost, good performance in the mid-infrared, possibility to make some complex sensors with low power consumption. And in the Cornerstone MPWs, we offer 3 platforms. That's 500 nanometer SOI, and you can use this platform up to 4 microns, because beyond 4 microns, oxide becomes very lossy. Then we can suspend this silicon, so remove silicon dioxide and get suspended silicon. So that will enable us to explore the entire transparency range of silicon, which is up to almost 8 microns. Then we can use germanium and silicon. If we grow germanium on top of silicon and then etch a form waveguide, that could give us good or low loss up to 10 or 11 microns. And we can also suspend germanium, so remove silicon and get germanium membranes, which would enable us to use this up to 14 or 15 microns. So in Cornerstone, we offer these 3 platforms: SOI, 500 nanometer SOI, suspended silicon, and germanium on silicon. And when you think about waveguides for sensing, obviously we want to, in some cases, to have large evanescent field. Let's say it's gas sensing. We want the optical mode to interact with the gas that surrounds the waveguide. So confinement factor or evanescent field, the proportion of evanescent field is important. And also we want these waveguides to be low loss, such that we can have a large spirals, we can have tens of centimeters or maybe even the order of meter. waveguide such that there is a large interaction length between the optical mode and an analyte. So figure of merit could be this evanescent field over the loss. If you visit Cornerstone website, you can find out when next calls are for SOI suspended silicon and germanium silicon. So I'll just give you a couple of examples how we can use SOI mid-infrared platform, 500 nanometer SOI. See the work that one of our PhD students did a couple of years ago, where she detected IPA in water at the wavelength of 3.77 when there is a large absorption peak. The limit of detection was 1%. But what was interesting, what she used is this switch here. So we have a sensor waveguide with open window. So that's where the optical mode interacts with IPA. And then we have reference waveguide, which is covered with cladding. So there is no interaction with IPA in water. And then by using this heater, we can switch between sensor and waveguide, reference waveguide. And by using just one detector, we can get this limit of detection. And the noise floor was reduced by a factor of 11 compared to a simple waveguide sensor. Another nice example of using 500 nanometer as mid-infrared platform was sub-ppm level, parts per million detection of methane at 3.3 microns using slot waveguide. So slot waveguide has this gap between two silicon parts. In this case, it was 150 nanometers. So you can see that the light can interact a lot with methane present in the environment. And that was work reported by Jana Jagerska's group in Tromsø. Okay, now let's say we want to detect carbon dioxide or nitrous oxide. So those are the two gases that I previously mentioned. And we need to have some platforms that operate at 4.2 or 4.5, 4.6 microns. And I've already told you in that case, oxide becomes quite lossy. So we could use suspended silicon. And we can take two approaches. One, where we etch rib waveguide. So we form first the waveguide. And then we etch these holes, which are relatively far away from the waveguide, such that the optical mode is not disturbed. And then we use these openings, these holes, to remove the oxide underneath. So we can suspend this, and this is work from Hon Kin Seng group in Hong Kong, where they demonstrated these suspended silicon waveguides at a wavelength of 2.75 microns. What we have done in collaboration with University of Malaga and NRC in Canada, and which is now, you can now send your designs to Cornerstone and get some chips, is a different approach where we have these holes very close to the waveguide. However, these gratings, as you can see on the side, are so-called sub-wavelength gratings, so they're much smaller than the operating wavelength. So the light basically, excuse me, will see this just as an average refractive index. So we'll get this confinement, lateral confinement, and then we can use this hole to, with some wet etcher to remove, to suspend silicon and to get a suspended waveguide. Why we think this approach is better than the previous one? First, we use just one dry etch step to form these holes. Secondly, let's say gas now can be closer to the waveguide, so we can have larger interaction with the gas. It can also be more mechanically stable because we are using the total thickness of the wafer, which is 500 nanometers. So we don't thin this region here to form the rib waveguide. And you can hardly see, but there is some sagging. There is bending of this structure. because this part here is quite thin. So we're using the full thickness of the wafer. And there are now a lot of parameters that we need to take care of. What's the period? We said the period should be small. What's the opening here? What's the hole size? Because if we use liquid etchant, then that liquid should go through that hole and remove the oxide. Of course, we can use vapor etch method, but that's a bit slower. Then we also want to have large interactions, so large evanescent field, but at the same time, we want to have leakage of the mode into the slab, and so on and so forth. And of course, the immediate thing is to consider mechanical stability. So can this structure sustain vibrations or certain pressure, and so on. So it's important to consider that. So what's the fabrication of these structures? As I said, we first do dry etch to define these gratings, and then we use HF, liquid etchant, to remove the oxide. So that etchant will just attack oxide, but won't etch silicon, and then we get air gaps here. In some cases, we also want to use pre-concentrator. So let's say that we cannot get large lengths on our chip, and we need to reach certain limit of detection, which is quite small. Then we can cover our waveguide with certain polymer. That polymer can contain so-called cage molecules, which will attract, let's say, methane, that's tryptophan A. And it can also repel water, because water absorbs a lot in the mid-infrared. So we can get these methane molecules close to the waveguide, but no water there. And that's how we can reduce limit of detection, get better performance of our sensors. We have demonstrated a range of passive devices, so you can see bands and asymmetric Mach-Zehnder interferometers and 2x2 MMIs and directional couplers. And this is also grating coupler. You see fully suspended over 50 microns or so. And you can see some very good numbers in terms of the loss, around 1 dB at the wavelength ranges where we have these gases, their absorptions, and slightly larger at 7.7 microns. But I need to mention that at this particular wavelength, we already have 2 dBs per centimeter material loss from silicon. So if you subtract that, we're again about 1 dB per centimeter in terms of the scattering fabrication related losses. Bands, MMIs, Mach-Zehders, very, very good numbers. And we have designs for methane, for nitrous oxide, for carbon dioxide, which can be used. Now, if we want to move further, let's say we want to detect some proteins in the mid-infrared. Those are larger wavelengths, so let's say from 6 to 10 microns. Then we can extend the operating wavelength range by using germanium and silicon. So you can see we can grow germanium on silicon substrate. And these are some of the losses that we've got here in Southampton. So very good numbers up to roughly 8 microns. Of course, after that, we have a part of the mode propagating through silicon. We also have some threading dislocations, which I'll mention in a minute, and that contributes to larger losses at longer wavelengths. We demonstrated ring resonators, a Vernier type, and also some efficient grating couplers. And in this particular structure, we don't have a large refractive index difference between germanium and silicon, so efficiency of these gratings can be compromised. And also, we could see that in some cases we got a lot of reflection back. So with Carlos Alonso Ramos from Paris, Saclay, we demonstrated some inverted grating couplers where the mode is pushed into the slab and then coupled into the fiber. And by doing that, we reduce the reflection. And this is image of the fabricated device. So we use this platform, germanium on silicon, to see, classical amide 1, 2, and 3 absorption peaks of proteins. So that was BSA and PBC solution. What we did, we used just multimode germanium waveguide. We put filter paper, cover that with cover slide with slip, and then we pipetted BSA and PBC that propagated through the filter paper, came to in contact with the germanium waveguide, and then by doing these scans, we could see characteristic peaks. We also investigated how this changes for monomer, oligomer type of proteins, and basically that can be used as kind of biomarkers for early diagnostics of neurodegenerative diseases or cancer. So it's a very important piece of work. I also want to point out another example where researchers from EPFL in Switzerland use germanium and silicon platform to detect cocaine in human saliva. They also integrated the chip with microfluidic-based liquid-liquid extraction system. So basically, they transferred cocaine from saliva, which contains water and so absorbs a lot in the mid-infrared, to tetrachloroethylene, which is transparent mid-infrared transparent solvent, and then that solvent with cocaine was led to the germanium waveguide, and they got limit of detection of 100 grams. Sorry, this should be grams per milliliter, which again can be improved significantly, but that was kind of first demonstration. So what's the problem with germanium and silicon? Germanium, when you grow it on silicon, because it has different lattice constant, after certain thickness, of course, it's strained, and to release that strain, we get dislocations appearing, and that dislocation contribute to a loss. And the best material has about 10 to 6 of these dislocations per centimeter square. So another approach how that can be mitigated was shown by the Mars Morini group and Giovanni Sella, first from Paris, second from Como in Italy, where they use this graded silicon germanium. So they start with silicon and then gradually change the concentration of germanium, ended up with something like around 80%. So the mode will be pushed upwards, and we can see this is quite thick structure, and won't see much of these threading dislocations or silicon indeed. So they got some really broadband devices. And finally, we can use suspended germanium. So either use TMAH etchant to remove silicon underneath the germanium, or what actually we've done, we thinned down SOI to 40 to 60 nanometers. Then there was growth of germanium on top of that thin SOI. And then we use both HF and TMAH. TMAH would remove silicon and HF oxide, and then we would get the suspended silicon. Or we also, in collaboration with Malaga, demonstrated some sub-wavelength grating germanium. So with just one etch step. And again, decent numbers for the loss. So how we can use some of these structures. Let's say in therapeutic drug monitoring, where we want to monitor certain drugs in blood. Low concentration of that drug that treats certain condition is ineffective. Large concentration can be very dangerous. So there is a clinical need to monitor that constantly in a very short span. And we believe that silicon or germanium photonics could be useful. So you can imagine there could be some even disposable sensor that you can slot into this device. First with some blood, could be whole blood, but most likely some serum or plasma. And then we get detection of the presence of these drugs. Another example is that protein sensing that I just mentioned for cancer screening. In this case, we're working with the hospital in Southampton on lung cancer. And finally, you see these kind of robots that like torpedoes that float on an ocean surface, or can actually go also deep into the ocean. And they want to measure a concentration of gases. those three that I already mentioned. So in this case, sensor must be very small, low power consumption. So we think that silicon or germanium chips can be very useful for that. And we address these needs in the mission program grant funded by BSRC. So in terms of sensing, we can have two scenarios. Either we have tunable laser, and then we split light into two arms. So we need splitter, we need waveguides. Reference arm is covered with cladding. So there is no interaction with an analyte, and then we open sensing window in the other arm, and then we have reading from two detectors and compare them and find what's the concentration of that analyte. Or we can have a broadband source, some spectrometer on chip, and then integrated detectors, and again retrieve what the input signal was or what kind of absorption we have. So in this particular case for broadband operation, we need broadband waveguides. Again, by using some metamaterials, some 2D gratings, we have shown that we can have single mode operation over almost 2 microns, so from 2 to 3.8 microns with really nice loss. The trick here is that effective index of the cladding is close, so this is orange curve here. It's close to the effective index of the fundamental mode. So all higher order modes will just leak through this cladding and will retain single mode operation over large bandwidth. And you can see the fabricated, the top image of the fabricated waveguide. We've also done some work on broadband splitters. So again, if we want broadband devices, our splitters should be broadband. So this is an interesting approach where we have 13 segments. So these widths are optimized such that splitter can operate over almost 1 micron in bandwidth, but also more importantly can be resistant to scattering even if this tip is 200 nanometer wide. So you can see this is standard Y splitter without these segments. You can see a lot of scattering at the tip, but in our case, not so much scattering. So the loss is actually excellent over this bandwidth. Another splitter that we very often use in silicon photonics is MMI. So we can split 50-50 in 2 arms. Usually MMI is made of solid silicon, so all this is silicon, but in this case we have sub-wavelength grating silicon here. And we have shown by doing that we can increase the bandwidth, the operation wavelength of our MMI by a factor of 2. So you can see to have imbalance, small insertion loss, and so on, the conventional one would operate within 300 nanometers, but the SWG structure over 600 nanometers, so we can double that. In terms of the spectrometers, this is the first mid-infrared spectrometers that we have demonstrated in 2015 with NRC and Institute of Optics in Madrid. And by using 42 Mach Zenders with different path lengths, so you can see all are asymmetric, and by measuring the output, we can retrieve the input signal. So we got spectrometers on chip, and if we have large difference between these arms in the Mach Zender, we can get good resolution. But we need also small changes to get large bandwidth. So Delphine's group in Paris, they combined these two approaches in their braided silicon. So they have these asymmetric Mach Zender, but also they integrated heaters such that they can smallly tune the phase between the 2 arms, and then they also got good bandwidth. So finally, what about detectors? We need detectors at the end. So there are a few approaches. We can either use silicon defect-mediated detectors. So although silicon is transparent in that wavelength range, we have shown in some other groups as well that by deliberately making defects, in this case deep vacancies in silicon, we can get mid-band gap states, and longer wavelengths can be detected, 2 microns or even longer. In germanium, that can be also done. And because of strain and some dislocations, there were some good results at 2 microns, and Miloš and his team, they even got up to almost 4 microns. Germanium tin is an interesting alloy, and there are some good results between 2 and 3 microns in terms of detection. We can also use 3.5s. They are always good materials, so we can either bond them or flip chip them or transfer print. So that's a very popular approach these days. Again, graphene, very wideband coverage in terms of the detection, but of course, the main problem is the yield. And finally, thermal detectors like bolometers. So I'll just show one slide on that. This is our approach. So what is bolometer? Basically, it's a membrane made of amorphous silicon or vanadium oxide, which is thermally isolated. And then when the light is incident, so this is normal incidence, it heats the membrane, and that changes the resistance of the membrane, which we can measure. So the material should have large coefficient of resistance. But this is normal incidence. So if we want bolometer integrated in a waveguide, we can use our suspended structure, as you can see. So this is our waveguide. And then we make this bridge here in blue color, which is a amorphous silicon bridge. And we have contacts on the side. So when the light is propagating, if we add these antennas here, they can increase the absorption in this region, so they can heat this thermometer made of amorphous silicon. The amorphous silicon will change its resistance, and then we can measure that and measure the input power in the waveguide. And what about the laser as the last device? Do we really need laser on a chip? In some cases, we don't need that. I've already told you about disposable chips. So inside this box, we could have a high-end detector and laser, and that just slot in our chip, do measurements, and so on. So in medicine, the cost of this device can be large. But in some other cases, like in gas sensing in these robots here, we need something really small that can be integrated with electronics and motors and pumps and so on, with low power consumption. And in this case, we probably need laser on a chip. Laser can be, present on chip by direct growth. Montpellier, for example, have done this. Direct growth of mid-infrared lasers on chip, either through bonding or flip chip. We've done some work on that, or transfer print. So finally, summary, there is a huge potential of this field. We can really say that it's immature technology compared to the near-infrared silicon photonics. So the lasers are not as good, detectors as well. We still need to work on low-loss devices. There are several material platforms, so no clear favorite, like maybe near-infrared, where we have SOI. We also need to do a bit more work on transparent claddings. So if we want to open these sensing windows, what materials we can use? Are they resistant to some chemicals and so on? And we can also, in some cases, need to deal with pre-concentration, so to increase the concentration of certain alloys. So really the focus these days is on integration of passive and active devices, on electronics and pumps and microfluidics channel, putting that all in some systems, and also using machine learning and AI, because some of these spectra are hugely complex. So you can imagine in blood, you can have a lot of things from cells to lipids and so on. My last slide is about the 9th EPICS Fab Silicon Photonics Summer School. So you can find more about not just mid-infrared silicon photonics or space applications that Milos will tell you about, but also about various other fields in silicon photonics. We are hosting that summer school from 24th to 28th of June. We have a really good list of speakers, some outstanding speakers from industry like Intel and IMEC and Point Cloud, IR Labs, and so on, but also from leading universities that have excellent research groups like Ghent and Southampton, Paris-Saclay, Malaga, Politecnico di Milano, Barcelona, Cardiff, Tyndall, etc. And there will be some social events and lab tours and trips and quizzes. So I really hope that many of you will join us at the end of June in Southampton. That's all for me. Thank you very much for your attention.